In this lecture, we will take a look at the tuned radio frequency receiver, the TRF receiver. We will take a look at the relationship between two aspects of a receiver, one being the tunability and the other being the selectivity of a receiver. We will take a look at an example to illustrate that dependence of these two parameters of a filter, the tunability and the selectivity. Then we will take a look at a powerful receiver called the Superheterodyne receiver, which strikes a balance between these two aspects. Again, the tunability and the selectivity of a receiver that is based on using a bandpass filter or maybe multiple bandpass filters. So this is another way to extract the message from the carrier by using a bandpass filter. In the previous lecture on communication systems, we saw that we can either use a synchronous demodulation by using a local oscillator in the receiver to extract the message from the carrier. This requires the local oscillators at the transmitter and receiver to have a phase synchronization. And the other scheme that we looked at was the asynchronous demodulation, which was based off of a envelope detector constructed using a simple diode. This is another way to extract the message from a carrier. So what we have here is a sound application. We get the received signal using the receive antenna. We amplify the RF signal first, go through a detector which has a bandpass filter to extract the things, and then we will also have to follow the bandpass filter up with another demodulation. So we may use an asynchronous demodulation after that. And then we have an audio amplifier which drives the speaker. Ideally, we would want the bandpass filter to be highly selective. And we would want that so that we can differentiate between the desired signal and all the other signals and noise. So how does a highly selective bandpass filter look like? Well, for that, I'm going to draw a simple sketch over here to show how an ideal bandpass filter would look like. So maybe I'm just going to show the positive frequencies here. There is going to be even symmetry for you to be able to sketch the same thing on the other side. Now I'm going to have my x-axis as omega, and say on my y-axis I want to observe the magnitude of the transfer function here, or in this case it's the magnitude of the frequency response of the bandpass filter. So if I want this to be ideal and I want to say pass frequencies between some omega 1 and omega 2, I would want it to be a rectangle between those two frequencies and nothing else gets through it. So this would be my omega 1 and this would be my omega 2, and say the height over here is 1. So that would be an ideal bandpass filter that allows frequencies between omega 1 and omega 2 to go through, right? So that's how I'm doing the selection of that desired signal, which means that's what I'm using to extract the message from the carrier. Notice after we do this, we still will need an asynchronous demodulation scheme to down convert the signal to DC, and that is what drives the speaker and the audio amplifier. So that step is not being shown here explicitly. But so coming back to the selectivity aspect, if I want this to be highly selective, then I want this to be a rectangle in frequency domain. This is omega. And this is the absolute of the frequency, the magnitude of the frequency response, h of omega. How does a not so selective frequency response look like? Let me draw that in blue. So if I wanted to, again, tune it to a certain frequency, omega sub r, for example, resonant frequency omega sub r, and a not so selective filter would probably look something like this. It would have a pass band it would have a transition band, and it would have a stop band. But clearly you can see that it is allowing the desired signal to go through it, but it is also allowing all the other signals to go through it, and it may also allow noise to go through it. So that's not what we want. Ideally, we want that to be a rectangle in the frequency in order to make it very, very selective. But it turns out if you go for increasing selectivity, you lose tunability. And if you go for tunability, then you lose selectivity. So these have an inverse relationship that we will demonstrate on the next slide. Selectivity essentially means the ability to differentiate between the desired signal and all the other signals. So we are talking about that in terms of a rectangle in frequency domain, right? Filtering things out. Now, how do you make a bandpass filter? So the more selective it needs to be, the more stages that bandpass filter will have. Though it will be of a higher order. Over here, we are simply constructing this LC bandpass filter using some resistors, but one inductor and one capacitor. The input is shown as V in here, and output is being measured across R2. So how do I find the frequency response of this filter, bandpass filter? How do I derive that? Well, you would need the impedance of these elements. So I can write that as R1 here, J omega L over here, 1 over J omega C over there, and R2 over here. Once I write these impedances of these ideal components, then I can use a voltage division rule to write VO of omega divided by VI of omega, right? So that would be my H of omega. That would be my frequency response of this bandpass filter. So I hope from the knowledge of circuits you are able to do this step. But once you have this H of omega, we can try to sketch that as a function of omega, and realistically it is probably going to look like this. So it's not a rectangle. It is not. So it has some selectivity between a lower cutoff frequency omega LC and a higher cutoff frequency omega sub HC. The resonant frequency over here is omega sub R, which is related to the elements, the components that are being used here. Omega sub R, the resonant frequency is 1 divided by square root of LC. We can analytically find that out by taking the H of omega function, differentiating it with respect to omega, and setting that equal to 0. Once we set that equal to 0 and solve for omega, that makes it go to a peak. That's how you can find out omega sub R. So the value at which H of omega goes to a maximum. Differentiate it with respect to omega, equate it to 0, find the omega that makes it happen. And you should get that equal to 1 over square root LC, but it is also dependent on the lower cutoff and higher cutoff. So it's actually the geometric mean of the lower cutoff and the higher cutoff. So you can also write, let's see, over here, I can say omega sub R, which is my resonant frequency of the bandpass filter, can be written as square root of omega LC multiplied by omega HC, geometric mean. Let's see, and clearly the bandwidth is omega HC here minus omega LC. That would be the bandwidth of the filter, which has to kind of match the bandwidth of the desired signal, so that it is only able to pick those frequencies up and reject everything else. How do I derive the upper and lower cutoff? Well, if you know the maximum value, let us suppose this is 1, say, then it would be 1 divided by square root 2. So we are going for half power bandwidth here. So if it is half in terms of power, in terms of the frequency response, it would be divided by square root 2. And if you know the function h of omega and you know the value of the amplitude here, 1 over square root 2, so the frequencies for which the magnitude of the frequency response goes to 1 over square root 2 are going to be derived using a quadratic equation. You need to solve that to get two frequencies, omega hc and omega lc. So that's how you would analytically derive those two frequencies. Now, with all these aspects of the filter, how good is the filter? How selective is the filter? You know that by evaluating the Q factor or the quality factor of the bandpass filter here, which is essentially the ratio of the resonant frequency in hertz, FR, F sub R. So you would divide that omega sub R by 2 pi to get the F sub R. Resonant frequency divided by the bandwidth of the bandpass filter. That would give you the Q factor, the quality factor. Higher the quality factor, higher the selectivity, right? Because if you want that to be of really high quality, that would mean that you would be very selective to pick out those frequencies. Now, F sub R and bandwidth are related to LNC, as you have seen, which means that if I make my bandpass filter, if I design it, if I actually build it out, my Q factor is set, which means my resonant frequency and bandwidth now are more or less limited now, right? I will not be able to move it around without affecting the other. So note that point here, that the quality factor, once you know which frequencies to tune to and you have fixed those frequencies, you build the filter. Once you build the filter, the quality factor will be set. All right, so let's move on to the next slide here. We have the selectivity issue of the tuned radio frequency receiver. We are going to start with tuning to an AM band at 1000 kilohertz first. And once after we tune this, we will try to see if it can be tuned to 550 kilohertz, and then we will see if we can tune to a different frequency. So we are trying to change the center frequency of the bandpass filter, the resonant frequency of the bandpass filter, and we'll see in this example what are its consequences, right? So let's start with number one. Let's tune at 1000 kilohertz. So if you see 1000 kilohertz, we'll start off with an assumption. The assumption is our signal of interest has a bandwidth of 10 kilohertz. So the signal of interest has a bandwidth of 10 kilohertz. I'm tuning to 1000 kilohertz, which means the quality factor of this filter should be FR divided by bandwidth, which comes out to be 100. Once I know this factor, then I will design my bandpass filter, meaning I will pick out the values of L and C that make this happen. I will design the filter after that. Now, if I go on to tune to step number 2, I'm limited by the same Q here, right? So because I've already made the filter, I'm restricted by that now. Now let us see if I can actually tune to a different frequency in the amplitude modulation band, AM band of 550 kilohertz. Can I tune it? Well, if I want to tune it, my Q is set to 100, and I'm trying to tune to 550, so my resonant frequency should be at 550 kilohertz, which means that my bandwidth, which is related to the resonant frequency and the quality factor, is now 5.5 kilohertz. It is too small for the signal, which means, what did I just do? I said that my signal has a bandwidth of 10 kilohertz, right? And that is going through this bandpass filter of the same bandwidth. But the moment I tuned it to a different frequency, the bandwidth of the bandpass filter almost became half, which means that I will be essentially chopping off half of the signal of interest, right? So bandwidth of the filter is too small now. I am not filtering the complete signal. Actually, I am rejecting part of the signal of interest, which leads to fidelity of reception is poor, right? So I'm losing some of my signal. Now, if you think about the maximum voice frequency, in this case, if the filter is able to extract frequencies only up till 5.5 kilohertz, that's the highest frequency of the signal that is getting through this filter, Then if you divide that by 2 because of Nyquist criteria, we will take a look at that in the next lecture here. The maximum voice frequency that is able to get through this filter is only 2.75 kilohertz. And everything above that are being rejected by the bandpass filter here. So big picture, step number 2 leads to bandwidth of the bandpass filter being too small and you actually losing the signal of interest, which you didn't want that to happen. Now, instead of going from 1 to 2, actually let's try to see if we can go from 1 to 3. Right. So we are trying to tune here instead. So our resonant frequency in this case is 1550. Can I do 1550 after having made my bandpass filter of quality factor of 100? Let's see that. Q is set to 100. What would be the bandwidth? If FR has changed to 1550, what would be the Q? Q is also set to 100. What would be the bandwidth? Now the bandwidth has increased to 15.5 kilohertz. Too big. What is the problem with the bandpass filter bandwidth being too big? Well, if it is too large, then it will allow the desired signal to go through it, which is good. However, it will also allow some noise to get through it. So it will pick up unwanted out-of-band noise. That is essentially between the 10 kilohertz and the 15.5 kilohertz mark. So we don't want that to happen. We want that selective filter to be rectangle only around the signal. So I hope you see that selectivity, by this example, you see that if I made the filter selective, I was not able to do the tuning. But if I made the thing very tunable, I would not have been very selective. So there is an inverse relationship at play with respect to these two aspects of tunability and selectivity of a bandpass filter that are resolved in a super heterodyne receiver, which actually gets benefits of both. And we do that by doing it in stages. Let's do tunability first and then focus on selectivity. So we get the best of both worlds by doing that. Now to go to super heterodyne receiver and show you the benefits of doing it in 2 stages, we will start talking about frequency division multiplexing. And frequency division multiplexing is an idea in which we share the resource of frequency. We have talked about how FCC plays a role in the most expensive resource that is available to us, which is the frequency, the spectrum. So by sharing the frequency, we can transmit multiple signals at the same time. There are other forms of sharing as well. So we can share the resource of time. User 1 speaks, after that user 2 speaks, and then after that user 3 speaks, and so on. That's time division multiplexing. There is space division multiplexing. There is phase multiplexing. So there is power. There's multiplexing we could do in power resource. But over here, we are focusing on the frequency division multiplexing aspect. So how can I share the resource of frequency? So can I use multiple resources, multiple channels, and can I spread them out in the spectrum? So let's take a look at 3 signals that are being shared here. The frequency resource is being shared between 3 resources here. They are in time domain called x sub a, x sub b, x sub c of t. Those are in time domain. So these are 3 arbitrary time signals. Their Fourier transform is also written as cap x of sub a of omega, cap x sub b of omega, and cap x sub c of omega in red, green, and blue respectively. And their Fourier transforms are sketched over here in 3 different shapes just to identify which one is which. And for the sake of convenience, we have chosen the maximum frequency in each of these 3 signals to be the same. Omega sub m is the maximum frequency here. They're all baseband signals, A, B, and C. And we are trying to share the resource of frequency. So how do I share it? Well, I multiply the first signal with cosine omega sub a. When I do that, what happens? So let me erase these blue things first, and then we can color code the rest. All right. So for omega sub a, yes, let's use yellow. So when I multiply x sub a with omega sub a, I'm essentially taking the spectrum of x sub a and moving it up and down by omega sub a, thereby getting these two pieces. Multiplication by cosine results in convolution of the triangle with two impulses present at omega sub a and minus omega sub a with a weight of pi. So that's exactly how you're getting those two rectangles. Then you add that up with, so that's what we are calling y sub a of t. And it gets added up with what? It gets added up with x sub b multiplied by cosine omega sub b, which is this rectangle getting moved to plus and minus omega sub b here and here because of that multiplication. And it's getting added up with the trapezoid x sub c multiplied by cosine omega sub c. So the trapezoid moves up and down by omega sub c, giving you those two pieces there. And we have sketched the final spectrum here, which is indicated by capital W of omega. We have sketched that on the frequency scale. At the x-axis is omega over here. And you can clearly see that these three signals are sharing the resource of frequency. And there are other aspects of this we could discuss as well, which is, can this be closer together? Yes, they can be very close to each other. The problem with that is then they will start interfering with each other. They could be crosstalk. And also there could be problems in designing the filters that are extremely selective and only pick out one triangle or one rectangle. So yes, you can bring them close together, but a guard band between them is good insurance policy in order for the filters to not be burdened with the selectivity. Right? So we usually leave some amount of guard band between these individual spectra because there obviously is a practical filter that is filtering these out, which will have a transition band. So different signals are occupying different parts of the spectrum here, and we need to choose omega sub a and omega sub b and omega sub c such that there is no interference, there is no overlap in these things. Otherwise, the information on one signal could be corrupted by the information on the other signal, thereby losing both the signals. So we don't want that to happen. There are some certain cases where we could have an overlap in terms of their spectra, which is orthogonal frequency division multiplexing. In short, it's called OFDM, which is part of a higher level course. So you could actually make these signals XA, XB, XC orthogonal to each other and have an overlap in the frequency domain, so make them tighter so as to not pay too much money to the FCC. And you can do that as long as the signals are orthogonal to each other. But you have to have a different type of receiver for that. A simple bandpass filter will not work for that application. Okay, let's move on here. So suppose we have a frequency division multiplexed FDM signal, and we are trying to receive that using a superheterodyne receiver, also called as the Armstrong receiver. What are the two aspects of this receiver that I'm going to try to balance out? One is the tunability and the other is the selectivity. So in a superheterodyne receiver, we actually try to get the best of the both worlds, as I mentioned earlier. So the advantage over here is we get a constant selectivity over a wide range of frequencies. So the wide range of frequencies is addressing the tunability aspect of things, and constant selectivity is I will have a really good filter, very selective, and it will be constant for all the tuning, right? Like no matter if I tune here or here or here, my bandwidth of that filter will remain the same. That's what we are going after now. Okay, so let's see how we are doing this. We are doing this in two stages, like I said. The first stage here is highlighted in yellow. The first stage is, let us make a filter which is coarse tunable, and we are calling that filter frequency response as h sub 1 of omega. So it is coarse, meaning it is not very selective, so it's not a rectangle. It looks like this. This guy is the coarse filter. So it's not very selective, but if you want to move the tuning up and down very quickly, you can do that, right? So you can go up, in the order of tens of kilohertz if you wanted, so that the tunability is very coarse. Right? So the first stage is make things that are tunable, but coarse, and it's not very highly selective. So coarse, so highly tunable over a wide range of frequencies, but not very selective, as indicated by the trapezoid shape instead of a rectangle shape. So that's stage one. And you see what we are saying. We are saying that y of t is a frequency division multiplex signal. Our receiver gets that from an antenna. Y of t Fourier transform is y of omega. You are using a coarse tunable filter h1 of omega first, which is tuned to omega sub c. Omega sub c is the center frequency of that filter. Once you filter that out, we are calling that signal q sub t, and in frequency cap q of omega. We are multiplying this q of t with a cosine, not at omega c, but instead, here is the trick here for this, omega c plus omega sub f. Omega sub f is called the intermediate frequency. Omega sub f, or f sub if, some f sub if is in frequency, that's in radians per second. So there are two things, right? One is this guy is simply a cosine omega ct here. That's where we are getting that omega c from. So we are using that information omega c for this oscillator to generate a frequency that is omega c plus omega sub f. We multiply this with q of t in time domain, which means that in frequency they are getting convolved. You get z of t in frequency cap z of omega. Now you have your second stage of filtering, where this is now a fixed selective filter. So highly selective, meaning looks more of like a rectangle, but it is fixed, so it's not tunable. You set it at one frequency and you leave it there. You don't move it around. So coarse filter followed by a fixed filter. Tunable, very selective. So that's how we get the best of both worlds. And then after the fixed selective filter H2, you get R of t, which goes to a demodulator. So after that, you can use a asynchronous demodulation scheme like we did in the previous class, using an envelope detector to get back to baseband after that. So those are the two stages. Let us look at all the details in an example here. Now let's suppose that y of omega is this frequency division multiplexed signal. There are three signals here. One is in blue, one is in red, and the last one is in green. The Fourier transform of that frequency division multiplex signal, the thing that you receive, is shown over here. Now let us suppose that we are after this red piece. Let's suppose that out of these three signals, we want our superheterodyne receiver to extract the red part of this signal, which is the triangle. Those frequencies are labeled as omega sub c and omega c sub plus omega m and minus omega m, right? So this is the frequency at which we need to tune the first filter, and the second filter needs to have a bandwidth of at least 2 times omega m. That's the kind of information we get from there. So let us use the first, the coarse tunable filter. First, the receiver uses a coarse filter to extract the signal. Well, not exactly the signal. There will be some part of the blue and some part of the green that will get through this coarse filter because it's not highly selective. So if we assume that H1 of omega has a transfer, the frequency response like this, we are going to get omega C through, like the red guy goes through this. But as you can see, this guy, they're getting multiplied in frequency, by the way. But I hope you see that this part of the spectrum here overlaps with that region in the spectrum. This is going to overlap with that region over there, which means that after I multiply this rectangle is probably going to become, after multiplying, it will become a slope of going down. The triangle is where everything is flat, so that triangle will be preserved in shape, so that's fine. But this semicircle over here will have a slope on top of it once I multiply. So this might go down to 0 here and then come up. All right, let me erase these. And after I multiply, right, because I'm passing y of t through that filter, so in time it's getting convolved to get q of t, but in frequency it's getting multiplied. So let's take a look at what happens after you multiply. Also note that omega c can be tuned to different channels. So I could have picked omega c here or there, like I could have moved that omega c around. This guy, H1 of omega, will move around. It's a coarse filter, so it can move around very easily. Next, so after you multiply those in frequency, I hope you notice that this guy went down with a slope and this guy came down as well, but the triangle remained as is. Now, what is the next step? Once you have q of t or q of omega, you mix that, or you multiply that with cosine omega c plus omega f, right? Carrier frequency, or the center frequency of your coarse filter plus the intermediate frequency. So what happens after that? Whenever you multiply a spectrum with a cosine, that cosine obviously has a Fourier transform, which I can write in this form. Pi, one impulse at omega c plus omega f, one impulse at omega c minus omega c minus omega f. And obviously there will also be a 1 over 2 pi factor. So when you multiply q of omega with cosine, the entire q of omega will move up and down. You will have sum and difference frequencies with respect to omega c plus omega f, right? So I'm going to highlight those frequencies here. So let us say I am highlighting omega c here and omega c plus omega f here. The sum frequencies are going to be omega c plus omega f. So that would land at 2 omega c plus omega f right here. And then of course, when you do the other side, you will get negative 2 omega c negative omega f. Now, when you look at the difference frequencies, omega c will cancel out, and what you will be left with is omega f and negative omega f. Now, we can design that fixed band pass filter, which is highly selective at omega f, at the intermediate frequency. So now we consider the filter H2 of omega, which is fixed. It's always at omega f, intermediate frequency, and it has high quality factor, highly selective. As you can see here, I've drawn it up as a rectangle. So once I pass this z of omega through H2 of omega, everything will be cancelled out. So all of this will be cancelled out, and only these pieces will get through. And I'm also selecting the gain to be 2, which means that this half will become 1 there. All right, let me erase these so that there's no confusion. Now, how wide does that intermediate frequency, the H2 of omega needs to be? Well, that depends on the bandwidth of the signal. So we said all of these guys have omega c plus omega m, omega c minus omega m. So that needs to be at least 2 omega m wide, and that's how we are using it. omega f, center frequency, omega f plus omega m, omega f minus omega m, and so on. And once you filter on for the second time, you will get back your signal of interest. We said, let's do this for the red rectangle. Now we have the signal of interest. But it is not present at 0 at baseband, it is present at omega f. So what we would need is a asynchronous demodulation scheme to bring that down from omega f down to 0. For this, you can refer to the synchronous demodulation or the asynchronous demodulation from before, from the previous lecture, how to bring this down to 0 and extract the message out of that. But I hope you see the benefit of using coarse and selective filters, H1 and H2. This also means that suppose in a lab you had one really good filter, very selective filter. You make that the center frequency of that filter, you make that your intermediate frequency, omega f. And that's what you use your cosine as. Whatever you need to extract plus that intermediate frequency. So by changing the frequency of this oscillator, you will be able to pick out any signal, with the benefit that after the first stage, the result will fall in one region and one region only, where you have that high selective filter. So we are almost manipulating the spectrum in such a way that we force the result to fall in that highly selective filter region, so that we get coarse, the tunability aspect as well as the selectivity aspect. All right, so I hope that was clear. Now we'll do an example here. So we have a block diagram that is shown. You have x of t being multiplied with a carrier e to the j2t. The result is a of t gets low pass filtered with a cutoff omega sub c. The result is b of t that gets multiplied with another carrier e to the negative j2t. The result of that multiplication is z of t, and after that we are doing a 2 times real part of z, and that's our y of t. Our goal for this example is to find the transfer function, overall transfer function. So here is the input, here is the output, and after you divide the Fourier transform of the output divided by the input, you get your overall transfer function, y of omega divided by x of omega, which is essentially like saying, if you treated this entire thing as one block, one filter, we are saying that the transfer function of that is h of omega, right? Let me erase that. That's it. All right, so let's see how well h we have used. So all right, let's do this in unit operations, one operation at a time. How can I write? So on the left here, everything is time domain, and on the right here, everything is in the frequency domain. A of t can be written as x multiplied by e to the j2t. So x of t multiplied by e to the j2t. In the frequency domain, a of omega can be written as x of omega minus 2. Why? Because this is essentially the frequency shift property. You multiply in time domain by e to the j2t, there is going to be a shift of x of omega by 2. Next step, b of t can be obtained by convolving the frequency, by convolving the impulse response of this low pass filter with a of t. That's in time domain. In the frequency domain, that would be a multiplication operation. B of omega, cap b of omega, is low pass filter transfer function HL of omega multiplied by a of omega. A of omega is known from the earlier step. Next, z of t is b of t multiplied by e to the negative j2t, multiplication in time domain. What is that? That's a frequency shift in the frequency domain. Z of omega is cap b of omega plus 2. The last step here is y of t equals 2 times the real part of z of t. That's the last piece here. 2 times the real part of z of t can be written as z of t plus complex conjugate of z of t. We know that from the properties of complex numbers. Now, the Fourier transform of that is going to be y of omega equals z of omega for z of t plus complex conjugate of minus omega. That's the Fourier transform of z conjugate of omega, z conjugate of t. Z of omega, now we do the backtracking. Z of omega can be written as b of omega plus 2. Highlight in blue. Z of omega is b of omega plus 2. So we write that. And if I wanted z conjugate of minus omega, I would simply do b conjugate of minus omega plus 2. Now we go one more step back. I can write b of omega in terms of h sub l of omega and a of omega. That's what I'm doing here as well as over here. Then the last step is to write a of omega in terms of x. A of omega plus 2 written as x of omega minus 2 plus 2 there, and even for this step. Once I write these and I simplify in such a way that I get x on the right side, and so my goal is to write y of omega divided by x of omega. So I've already come very close to that, so because I'm after that ratio. So the last step will be to factor things out and divide. Also assume that x of t is real, and if you assume that x of t is real, you will have conjugate symmetry in x, and h sub l is real. That will make sure that your there will be conjugate symmetry for the transfer function of the low pass filter. Now if I use these two, then I will be able to do the next step, which is to take things that factor out x of omega from here and here. Y of omega can be written as h sub l of omega plus 2 from the previous step times x of omega after using conjugate symmetry, and also for the second piece here. Factor out x of omega, divide the left hand side, you get h sub l of omega plus 2 plus h sub l of omega minus 2, which can be sketched like this because we already know what h sub l looks like. So we shift it left, shift it right, add them up, you get center frequency of 2 here, negative 2 there. The width will be the same, whatever the width of this guy was, 2 omega c. So 2 omega c there. That will be your overall transfer function of this. All right, so that's an example that will help you with some homework problems, and that's all I have planned for this video.